Let's get going. Before I start, so for those of you who have not seen the main announcement which I put up for the test will be on Tuesday, the 28th of March, and it will be in person in Fesa Noble 1. Okay, so and the test will be based on what we did last week and what we're going to do today as well. So the first chapter and the second chapter, that's what the test will be based on. So it will be 10 questions, multiple choice, mixture of non-calculation and with some simple numbers to use. Okay, and there are no computer practicals for this part of the course. That's been replaced with the test. So if you have the computer practicals already on your timetable, then there's no need to show up. Okay. So what I would like to do today is finish this current chapter, but before I go back to the notes, I want to just go through a very quick summary to make sure that everybody is clear in terms of what we've been trying to do last week and also what we're going to do next today. So I will write on here for about 5-10 minutes, and I'll go back to the notes. So can you just keep quiet and talk to me, not to your friends, please? Thank you. Just ask me. Okay, so if you want to talk to your friend, just wait another 15 minutes. Right, so the next 5-10 minutes, I will do a quick summary, and if there are things you're still not sure about, then just put your hand up there. So the summary, as you can see there, so we'll be looking at beams in bending. I will just make a rough sketch of a simple beam. So I'm going to do the beam as simply supported. I'm not, so fix there, roller support there. With some load applied, it doesn't matter what the load is. So I'm going to assume I have a uniformly distributed load, Q, and a point load somewhere there, P. We know the beam is going to bend. So, and when the beam bends, it will probably deform like that and like that. And because of the shape of the deformed beam, we know we're going to have some bending moment. So, and what we've been trying to do is to answer 3 simple questions. The first one is, what is the bending moment at any point along the length of the beam? Okay, and I think you did that in your first year. We've done it again here because we will need that. And it's very clear the magnitude of the bending moment will depend on where you are along the length of the beam and the load that you've got there. And the second question is, which we are trying to find because of the shape of the deformed beam. We know that right here will be in tension, and right there will be in compression there. So because of the tension and compression, we are generating some stresses. We want to find what is the magnitude of the stress. At any point along the beam. And along and in the beam cross section. So that's the one we are trying to do on Friday, and I'll quickly go back to that once I've written the third one. We know the beam has deformed, so as from that rough shape, we know that the magnitude of the deflection, for example, there is greater than the deflection at that location. We also want to find what is the magnitude of the deflection along the length of the beam. And those are the three main questions. So that one is what we did last week, and also you've done in your first year. And the bending moment would depend on the load that you put in and where you are. And we're going to go back to this. This is the one that we derived on Friday, and the magnitude of the stress will also depend on where you are along the length of the beam, and also the load that you've put in. And when we come back tomorrow, and then we will start on doing this. So the beam, which I've done, there's get that to show. The beam which I've shown there can have different cross sections. So it can be a rectangular cross section, it can be a box, it can be a solid circle, it can be an I-beam. So there are different cross sections, and what we'll show is that in order to answer the first one does not depend on the type of cross section that you have. It doesn't matter what the type of the geometry of the cross section is. The magnitude of the bending moment only depends on the load and where you are in the beam. However, the stress and the deflection would depend on what type of cross section that you've got. So that is number 2 is the one I'm going to show now. That's the one that we were trying to do on Friday, and I will quickly summarize that again. So the bending stress at any location in a beam in bending will show that the stress is sigma at a distance y from the neutral axis of the beam equals the bending moment you have at the location, second moment of area of the cross section, and Young's modulus over the radius of curvature. The radius of curvature determines how much bend you've got in the beam. So because we are interested in the stress, so let me just that is the stress axis in Newton per meter squared. That is y distance from the neutral axis. So I will explain what the neutral axis is again. And m is the applied moment, where sigma is being determined. And I, as we know, second moment of area. So m is in Newton meters, I is in meter 4, and y is in meters because it is length. And E is our Young's modulus of the material. And that is Newton per meter squared. And R is radius of curvature. And that is in meters as well. So because we are mainly interested in the stress here, so I'm going to write the stress in terms of the bending moment and also in terms of the Young's modulus. So from that, we can say that our stress along the length of the beam is the moment where we are finding the stress distance from the neutral axis divided by I. So that is using the first two there. If I use this first and the last one, I can also say that stress is modulus distance from the neutral axis over R. And we've shown how to derive that, and based on the assumption that the material is linear elastic, it is homogeneous, and plane sections remain plane, and that the actual deformation is also very, very small. And one general concept which we went through, are we all okay with that? Yeah. So one general.
Sorry, could you only tell me what is the second moment of area in meters?
4. Yeah. So one concept which we went through which I want to explain again, which I'm not sure we all got last week, because we'll be doing it again and again, and also in your 2 courses next year. So one is that so all internal stresses must be in equilibrium with externally applied load. So that is because when you apply a load to a structure, the load results in deformation and some stresses within that particular structure. But whatever stresses that you develop must be in the equilibrium with the load that you are putting onto the structure. One simple way of illustrating that is, so I'll just illustrate that before I go back to the beam. Just to explain that again, so I'm going to use a rectangular cross-section of a simple structure where we apply a force F and force F there, and this length here is A and that length here is B. So what is the stress? What is the stress in that bar in terms of F and A and B? 0? You see? Right. What is it? It's not 0, definitely. Sorry, force? Force over area. You've done your tensile test. This is like a simple test that you did in your first year. So the stress is force over area, which is force over AB. And that will be the same everywhere within that bar. What I'm going to show now is that has come from that. So we know we're going to have some stresses in that bar. So if I cut the bar to expose the main area where the stress is acting. So if I make a cut like that, so I've made a cut somewhere along the length, I've taken away the one at the top, I am left with the one at the base. So what we will be left with will be something like that. Now I still have my force there, F. So that was in equilibrium. This is no more in equilibrium as it is. But the only way it's going to be in equilibrium is if I have that stress that we are trying to determine acting everywhere on that surface. So the stress acts on that surface that is now outside there. So that is my sigma. So now I want to relate sigma to the force and the length that we've got. So I'm going to make that my x direction, and I'm going to make this my y direction. So remember we said this is length A and that is length B. So based on the concept that we've said there, that all internal stresses must be in equilibrium with the load that you are putting onto the structure. The load we are putting onto the structure is this. Sigma is my internal stress. So if I take a very small surface there, which has got a length dx along here and a length dy along here. So small area is dx dy. So that small area will have a small force that is acting on it. So that small force is sigma multiplied by dx dy. So in order to ensure we have that concept of equilibrium, so if I sum up all the forces that are developed by that stress on there, I must get back the force that I've got on that beam. So F must equal the integral from 0 to A of sigma dx dy and 0 to B dx dy. And if you are to do that, you will end up with sigma equals force over A times B. And that concept is the same in every engineering structure that is under basic static equilibrium. If we now take that and apply it to the beam, which we've been discussing, any question? If you take that and apply it to the beam, you okay? Yeah, just ask me. Yeah? No? Okay. So if you take that and apply it to the beam, a beam that is in bending, so a beam that is in bending, which we showed, let's just say the beam is in bending like that. So the only load we have on the beam is in this case, is only our bending moment M. So there is no load applied. Remember, the beam was initially straight, like that. That's the initial, and that's the deformed. So in the initial state, we are not applying any load along the length of the beam. So there is no load along the length of the beam. But because of the load that is applied transverse, we are applying the load perpendicular like that. So we've got the beam as a bent beam like that. But we've just said that if we take the neutral axis, which is the point along which there is no stress, we're going to have here stress which is positive along there. We're going to have here stress which is negative. Sorry. We have to, so at the top is under simple compression, at the bottom is under simple tension. So if we look right across that cross section, if I look along that cross section, so we will now have the neutral axis. We will have tension at the bottom and compression at the top. So what this is suggesting, here we have tension, and here we'll have it is in compression. So this is suggesting that we have stresses that are developed within the beam that are acting along the length of the beam. But we know we don't have any load that is applied. So what that means therefore is that if we sum up all the forces that are developed by the stress along the length of the beam, it must be zero. So if we take a very small length, say dy, and we find out what is the net force that is acting on that, and we sum that up along the whole of the beam cross section, we must have zero. So therefore, we'll say along the axial direction, sigma times the area of the cross section must be zero, since there is no axial force applied. So if we put that, if we use our relationship which we showed earlier, we can show therefore that sigma is EY over R dA. dA is the small area of the main cross section. And what this then showed is that because modulus is never zero, radius of curvature is not zero, what it needs to be zero, therefore, is the integral of Y dA is zero. Remember, Y is the distance from the neutral axis, so going downward here is our Y. So what that suggests, therefore, is that the force moment of area of the cross-section about the neutral axis is zero if you don't have any load applied along the length of the beam. But the load we are applying is the bending moment. We can do the same thing and take moment about the neutral axis of that small force. If we were to do that and sum it all up, we must get that moment that we have at the end there. So net moment will be, if I look at sigma times Y dA must be equal to m. So if we integrate from the base up to the top of the moment of the force, this force will have about the neutral axis, and then we can make that equal to 0. The same thing, we can substitute sigma in terms of modulus, so which means we have E all over R y squared dA equals m. So our second moment of area is that integral of y squared dA, and therefore that is where we got the final solution of the bending moment that we've got. So therefore we have. Sorry? Which one? This page? So both that and that are coming from the concept that the stresses that you develop within any structure must be in equilibrium with whatever load that you are applying to that particular structure. Okay, so that is the summary I want to give. So I'm going to rewrite the equation again, the bending equation m is that sigma over y equals m over I equals E over R. So let's now look at what we've just said. So moment of inertia I equals integral of y squared dA. And we've talked about neutral axis. So y is measured from the neutral axis, and we've also got centroid. So what is a centroid? Center of force, very close, not exactly. It's the center of area or the center of mass, okay? Right? So let's see how we find the centroid. We're going to show how we find the second moment of the area soon. So in order to find centroid, so if my centroid is at a distance y bar from a reference plane, then it's going to be given as the total area of the cross section and y dA. And the best way to explain this is to use an example. So I'm going to use an example of that. So if you have a cross section that is symmetric means so you have a center like that, and also like that, then the centroid is at the center, always, if cross-section is symmetric. So if the cross-section is that, then so your centroid is right there. But if the cross-section is not symmetric, so I'm going to show how we use this to find where that centroid is. So I'm going to use a cross-section that is a T cross-section. So let's assume we have something like that. Okay? So we have something like that, and we want to find the cross-section. We know it's not symmetric because if I draw a line here, so what is below is not the same as what is at the top. So I want to find where the centroid is. So I'm going to make the base my reference. I want to find how far from the base is my centroid. So remember what the centroid is. So that is my reference. So I would say y bar is integral of y dA all over A total. So with that, let me call that T1. That's thickness T1. So this will also be thickness T1. Let's call this thickness T2. Okay. So let's call the total height there, I'm going to call that L2, and I'm going to call this L1. Okay? So, my total area is the total area of that cross-section. In order to do that, the best thing is to divide it into different rectangular cross-sections. So I'm going to just cut this like that, and I'm going to call this 1, and I'm going to do the second one at the top. So the total area now we can easily find, because we can say that A total is L1 multiplied by T1. That is the area of the top. And the area of the vertical cross-section is going to be T2 multiplied by L2 minus T1. So we are finding what is the total surface area that we've got. So the top area is that length multiplied by the width, and the area of that is T2 multiplied by that height. So now I want to find what is that there. So what this is the dA is the surface area of each one, and Y is how far the center of the cross-section is from the base. So if I go to the top one, the area of the top one is L1 multiplied by T1. Okay? And the center here is at a distance of L2 minus T1 over 2. So the center is at that distance from the base. So our Y is how far is the center of the cross-section from the main base that you are using as your reference. If I go to the second one, I'll say plus the area of the second one is T2 multiplied by L2 minus T1. So that is the area. And what is Y in that case? We need to multiply by the distance from the base of the center of the cross-section. What should that be? So how far is the center of this vertical rectangle from the base? No one knows?
Sorry, I didn't get the question.
So how far is the center of this vertical rectangle? How far is the center from the base? Half L2?
Is it L2 minus half T2?
Minus half T2. Yes, L2 minus T1 over 2. Okay, that's good. So this height here, let me just use the color. So this height here, that height is L2 minus T1. Yeah. And so the center is basically half of that from the base. So we put that there, we'll say times L2 minus T1 over 2. And you can do that for any cross-section. You just decide what is your reference plane, and then you walk your way through. Okay, so is that clear? I want to go back to the note now, quickly finish and do the two basic examples that we've got. Clear? So in order to find the bending stress, therefore, we need to know what is the bending moment at the point that we want to find the value of the bending stress. And we need to know how far we are from the neutral axis, which is our Y, to be able to find that. So if you are on the positive side, then it will be tensile. If you are on the compression side, it will be in compression. there. Okay, so let's quickly move from back to the note. So this section here, which is what is called section modulus. Yeah, so section modulus here, what we use this for is if I have a choice between two beams, say one is an I-beam and one is a square beam, and I want to decide which one to use to minimize the magnitude of the bending stress if they are both subjected to the same load. And then we then refer to what is called section modulus there. It's not the same as Young's modulus because the units are not exactly the same. So we know that our bending stress depends on the moment, on the bending moment, the distance from the neutral axis, and the second moment of area. Sorry? All right, okay. I'm trying to show the whole page at once. All right, so okay, let's see if that works. Yeah. So we know that. So in order to find the bending stress, I need to know what the bending moment is and how far we are from the neutral axis, which is y, and what is the second moment of area of I for that particular cross section. But if we have a choice between 2 or 3 of the different cross sections, we know we're going to apply the same bending moment to them. We want to decide which one will give us the minimum stress, because we don't want the stress to be too high. That's where the section modulus comes. So if I use, I'm going to move that up. So if I have an I-beam, for example, so that's not symmetric, but it should be symmetric, and I have a square box. So my neutral axis, let's say my neutral axis is right here, and my neutral axis is right there. So the magnitude of the bending stress is going to be maximum where, remember, y is measured downward, so it's going to be maximum there, y maximum is here. And for this, the maximum y is here, y maximum is here. That's where it's going to be at this. So you go from the neutral axis to the main outer layer of your beam. So if the cross section is symmetric, so this distance from the neutral axis to where the tension is, and neutral axis to where your compression is, will be basically the same because you have a symmetric cross section. But if it is not symmetric, then this distance to the outer surface and the distance to the inner surface will not be the same. But if you use that principle, so we can relate that and find what is the maximum stress in tension and what is the maximum stress in compression, which is what we have here. And then that brings us what is called the section modulus, which is the second moment of area divided by the maximum distance that you've got between from the neutral axis to the surface of the beam. So if we have a choice, then we want to choose section modulus, which will ensure that the stress is not very high. So if I look at that, so I'm going to ask you to tell me what will happen if section modulus is very high and section modulus is very low. Which one will give us a greater stress?
Could you repeat the question, please?
So we have a section modulus Z, and that is the bending stress. If I have two beams, one has got one section modulus that is much greater than the section modulus of the second one. So which of the two will give us a lower stress? Is it the one with the higher section modulus or the one with the lower section modulus?
Section modulus is denoted by Z.
Yeah.
So the one with the higher modulus will give you lower stress.
Will give us lower stress. Great. So what will normally happen if you want to buy a beam of a particular cross section, whoever is selling that will tell you what is the section modulus of that particular cross section. And then you can then decide whether the section modulus of the beam is consistent with the load that you want your beam to take. Okay, so that's so I'm going to go and just do the next one, and I will solve the simple 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 example. We've discussed what happens if there is no load applied along the length of the beam. But there are some cases where you do have a load applied along the length of the beam. So that is one there where we have an axial force P and also a bending moment M. So we now have two loads. So we know what will happen if we apply just bending moment. But now what happens when we apply P? So what will be the stress along the length of the beam like that? So the stress along the length of the beam due to that force P acting will be P all over the cross-sectional area, which is A. So that is the force because it's like doing a uniaxial tensile test. And then the one due to bending will be M times Y, this time from the neutral axis over I. So we are now adding the two together. That is coming from applied bending, and that is coming from the force that you've put onto the beam. What does that mean? So what that means, therefore, is that if I look at what the stresses will look like, if I look at what is happening due to the force P, if I look at the cross-section, that is the neutral axis. So we will have a uniform stress because that force P is only giving us a uniform stress. So that is sigma equals P over A. So, and that is in tension because we are applying a tensile load. Yeah.
So My over I is, what is that? Is it a bending moment or what?
Which one?
My over I.
Yeah.
What is that? Is it a bending moment?
Yeah. So you have that applied.
Yeah.
So if you apply a bending moment, you get that beam will bend.
Yeah.
If the beam bends, you generate a stress. Remember what we've been discussing, if your beam bends like that. Right? So here is in tension. Here is in compression. Okay, and the neutral axis is right in the middle, has no stress. So that tensile stress is given by this, coming from the bending moment, how far you are from the neutral axis, and I is whatever geometry you've got for the particular cross-section. Okay. If I look at what the bending is doing, if you look at the bending, which is what we've done before, so we're going to have something that looks like this. So the stress is tensile on one side, and it is compression on the second side. So here is sigma equals my over I. Here is sigma equals minus my over I, because y is positive on one side and y is negative on the other side. But these two loads are basically acting together. So this is our neutral axis. So like I said, that is a neutral axis. So neutral axis is the axis along which there is no bending stress. Okay, so if you now put them together, because the two are acting together, so because of our that stress coming from the load P, then the center of the cross-section will no longer have zero stress. It's going to have some stress because of that load of coming from P. So what we now have will be coming from the center. That's the center now. So because of that P, we're going to now have So that is what we will now have. So the point where you now have no stress is no more at the center, because it's been shifted because of that. So this is now our new neutral axis. So the stress has changed that. And the point here is that so neutral axis and centroid. do not coincide if there is an axial load. So if you are applying a load along the length of the beam, then so your neutral axis and the centroid are not at the same point. But if there is no axial load applied, then your neutral axis and centroid will be at the same location, provided the cross section is a symmetric one. Okay, so let me just say. Right, so I'm going to solve. Yeah.
When you were drawing the graph out for the bending moment, how do you know that it starts at negative? How do you know the graph starts at negative? And then goes positive?
No, that's not the bending, but that is the stress. So if you bend, let me use this as an example. So if you bend this like that, if you bend that like that, so right, if you bend that upwards, so right here, right at the top, that will be in compression. At the base here will be in tension. If I continue to bend so far, then this will just break here because that tensile force is very high. So if you look at the here, as you go from the base to the top, you're going to be tensile, less tensile, less tensile, less tensile, become zero, and then compression, and more, and more. Okay, so I'm going to solve or go through the solution of an example. Probably I will do example two. Sorry? Yeah, that's the problem of this one. Right. So let's look at example 2.2, which is in the notes, so which I think should be relatively straightforward. So, but I'll go through that very quickly. Right. So, example 2.2, a beam in bending with uniformly distributed load, and we're asked to find what is the maximum bending stress. So let's see what that looks like. So that's the beam. The cross section is rectangular, uniformly distributed load. So we want to find the maximum bending stress. I will start. If assuming that you can see the base, and then I'll move up. Let's see what yeah. So we go. The bending stress is sigma equals the bending moment at the point we want to find the bending stress. Y distance from the neutral axis over I. Remember what the bending stress is. The bending stress is the stress that is acting along the length of the beam. Okay? It's the stress that is acting along the length of the beam. Right. And our Y, because of the rectangular cross-section, I neutral axis is through the center, and Y is measured downward from there. So if I want to find the bending stress, right here, my Y will be h over 2. So if I want to find the bending stress at the top, my Y will be minus h over 2. Okay. So that's what we've got. So in order to find the bending stress, I think here I want to find what is the maximum bending stress. So I will say maximum bending stress will be in that beam is wherever the bending moment is maximum, and the maximum value of Y all over I. So the maximum value of Y, because Y is going from the center, we know that Y max, in this case, is h over 2. And I, from the rectangular cross-section, is 1 over 12 b h cubed from the one that we've been given. So now what I now need is what is the maximum bending moment in the beam and where is that? So if you recall, we did that last week. So I need to find the maximum bending moment. So in order to find the maximum bending moment, we know exactly what we need to do. We need to find reaction forces. and then find bending moment equation at a let me just say from end A. So I'm going to just, if I just move that down a little bit. So let's call this A, let's call that B, and let's call the length of the beam L, like that. So that is what we did last week. So I'm not going to derive that again. I'll just write down what the bending moment is. If you recall from one of the example problem that we did, we said that the bending moment for this is M equals W x L over 2 minus W x squared over 2, where x is 0 to L. X starts from 0 to L. And it is maximum at the center for this particular case, so we can show that. So M max occur at the center of the beam. We did that in one of the solutions that we discussed at the lecture, I think on Tuesday last week. So, okay, so the maximum bending moment occurs at the center. So we have M max at x equals L over 2, and M max here equals, if I got that is WL squared over 8. I would say from stroke to 1 note. So if I want to find what is the maximum bending stress in the beam and where it occurs, then I cannot do that without knowing what the bending moment is. So that's why we started with that last week. So if I know the bending moment equation, I can find where it is maximum and therefore determine the value of the maximum bending stress there. If my interest, however, is just to find what the bending stress is at a given distance x there, not the maximum, then I need to know what is the bending moment at that point, and that bending moment there is what I will use here, and y is how far I am from the neutral axis, and I is the second moment of the particular cross section that we are dealing with. So I've got. Probably that's it. I was going to show how to find second moment of area, but I will do that on.
So what's the x?
No, I'm just saying if you are interested in finding what the bending moment is at a particular distance, where x say it could be 1 millimeter or 1 meter, then you need to know what the bending moment is at that particular point, because this is the bending moment due to this is the bending stress due to an applied bending moment at a particular location, at a given distance from the neutral axis. So,
And the neutral axis is where the centroid is.
sorry?
And the neutral axis, that's where the centroid is.
Well, yeah. If your cross section is symmetric, your centroid and the neutral axis are the same. If the cross section is not symmetric, then the centroid is not the same as your neutral axis. But this y is the distance from the neutral axis. Which page?
The next one. Yeah.
This one. Right. Who does not know how to find second moment of area here? Okay. Okay. So when we come back on tomorrow. So that's what we'll do first, and then we'll move on to the next one.